Okay, good evening and welcome to 24th lecture of IPA50 webinar series, New Horizons in Physics. I also take this opportunity to give you warm greetings on occasion of International Day of Women and Girls in Science, which was on 11th February. As many of you will know, United Nations declared 11th February as the International Day of Women and Girls in Science since 2016 to address the severe gender paucity problem in STEM. To mark the occasion, today we will have a lecture by one of the eminent women scientists in the country and the first Bhatnagar awardee in physics in India, and you will hear more about her from the today's coordinator, Dr. Himadri Dhar. Dr. Himadri Dhar is her first student. He did his PhD under guidance of Professor Manjari Ghosh and Professor Aditi Sen, and then he moved on to do his postdoc at Vienna University of Technology and at Imperial College London, and he is going to join IIT Bombay in 2 days time. As soon as he finishes his quarantine, he informs me. Here I should also mention he was a Lise Meitner fellow when he was in Vienna, so he has a very unique connection with a lot of women scientists. I now invite Himadri to introduce today's speaker. Over to you, Himadri.
Yeah, thank you. Yeah, can you hear me?
Yes.
Yeah, okay. Hello, everyone. Thank you, Professor Nanul, for the introduction and also for giving me the opportunity to chair the online seminar by such a distinguished scientist and my former supervisor, mentor, and close friend, Professor Aditi Sende. Before I begin, I would like to congratulate the Indian Physics Association for celebrating its 50th anniversary and for conducting this webinar series called New Horizons in Physics, which I believe will be really helpful for young people to get some access to interesting sites, especially during times when regular avenues for interaction are restricted due to the pandemic. Okay, so going forward, Professor Aditi Sende is a professor of physics and dean of student affairs at Harish Chandra Research Institute in Allahabad, now Prayagraj in India. To give you a brief introduction, Professor Aditi Sende was born in Kolkata and spent most of her early years in the city. She completed her bachelor's in mathematics from Bethune College and her master's in applied mathematics from the University of Calcutta. She then moved to Gdansk in Poland to work with Professor Marek Zukowski at the famous Institute of Theoretical Physics and Astrophysics, which now we know was one of the hotbeds of quantum information theory at that time. Here, her research was on manipulation of quantum states for quantum information and other non-classical applications. And she also happened to work with the famous group of Richard Horodecki, who have impeccable contributions to entanglement theory and quantum information in general. After her PhD in 2003, Aditi Sende, she won the prestigious Alexander von Humboldt Fellowship and moved to Hanover in Germany to work in the group of Professor Maciek Lewenstein. Thereafter, in 2005, she moved to the world-renowned Optics Institute, the ICFO, in Barcelona, where she was subsequently also awarded the Ramón y Cajal Fellowship, which is again a very prestigious tenure-track position and research grant by the Spanish government. But luckily for us, Professor Day returned to India in 2008 as an assistant professor at the School of Physical Sciences in JNU. And after a brief stint there in 2009, she moved to Harish Chandra Research Institute in then Allahabad, now Prayagraj, where along with Professor Ujjwal Sen and Professor Arun Kumar Pati, she started the Quantum Information and Computation Group. At HRI, she has been a part of an exciting research group where she has worked and supervised the thesis of more than 5 PhD scholars, including myself. And I think she also has 5 more scholars working with her right now. She has also worked with several postdoctoral scholars, several of whom have now gone on to hold independent faculty positions in India. She has published more than 140 papers in eminent journals, including 2 review articles and 2 book chapters. So Professor Day is among the few early physicists in India who championed research on quantum information theory and computation. In particular, her efforts have made incredible strides in quantum communication, quantification of entanglement, non-classical correlations, and other quantum information protocols. She has also worked on quantum cryptography protocols, and for creating quantum states for quantum computation and other aspects of quantum information theory. Now, a remarkable facet of her research was in her efforts to try and extend the conventional understanding of quantum information theory to other disciplines, such as many-body physics and quantum optics. As part of a group of international researchers, Professor Day extended knowledge from entanglement theory to understand things like dynamic phase transitions, properties of quantum spin chains, and multi-party entanglement in spin liquids. Moreover, she has also worked on methods to characterize and create non-classical quantum optical states for applications in quantum communication protocols, among other things. I think in general, she has championed the interest in quantum information and computation among the huge pool of young researchers in India, especially at a time when the topic was not so hot as it is today. And for her research efforts, she was awarded the Booty Foundation Award in 2012, and she also became the first female physicist to win the coveted Swanti Swarup Bhatnagar Award in 2018. So, while her research accomplishments are known to many, this introduction will be incomplete without saying something more about Professor De, or Aditi D as we call her fondly. Aditi D is a different human when it comes to our typical definition of a top scientist. Her humility and warmth as a person are simply remarkable. When we started our PhD, we were not quite accustomed to the kind of camaraderie and friendship between students and supervisors. And as most of us who have worked with her will readily agree, Aditi D tended to be a very good friend who stood by you in your difficult times, encouraged you to work hard, and also spent fun quality time with everyone, which was away from the usual rigmarole of research work. So it is a pleasure to know Aditi D simply as a lovely person, beyond her being a great scientist. So on the backdrop of International Day of Women in Science, it's my pleasure to introduce one of its torchbearers, Professor Aditi Sende. Yeah, Aditi.
Aditi, you're muted.
Sorry. Okay, so can you hear me?
Yes.
Yeah. Okay, thank you very much, Himanji, for such a touching introduction. So maybe I will share the screen and start my talk. So. Can you see my
Yes,
screen?
it's visible. Thank you.
Okay. So I first also would like to thank Indian Physics Association for giving me this opportunity to speak here. And it's a great pleasure that they are celebrating 50 years, and I can at least join in their celebration by giving this talk. So it's really a nice opportunity, and it's a very I mean, it's really my pleasure to be part of this. So today I'm going to, as Simadri discussed, so I work on quantum information science, and I will talk about technologies based on quantum mechanics, so quantum technologies. Uh, Before I go to to my talk, as Himadri described, I actually started my education from Kolkata. So I up to bachelor degree, I did my schooling up to 10th standard and then 12th, as well as up to bachelor of science from Bethune College. And all these schools and colleges are actually for women. And since, as Vandana said, that we are also celebrating the Women in Science on 11th February. So I must say that I belong to certain schools and colleges where I studied. They have a very big and nice history. So, for example, Sakhwat Memorial Government Girls High School, where I studied 11th and 12th. This was started by Begum Rokeya Sakhawat Hussain. She actually established this school in 1911, with 8 students, and it was one of the oldest school in Kolkata. Then Bethune College, where I did my bachelor degree, that college probably many of you have heard. This is one of the old women, I think the first women college in India, and from there the first graduate from the university, women graduate, who passed the graduations from University of Calcutta. And then later on, the first women scientist who actually got PhD degree from University of Calcutta also studied in Bethune College. So it has a very long history, which of course motivated many of us who studied there to do or to pursue the career in education, in teaching, in research, and etc. And after that, actually, I moved to master's degree in the University of Science College, that is University of Calcutta, and then went abroad for my PhD and postdoc. My thesis supervisor here, Marek Zhukovsky, and then I was with Maciek Levenstein in Spain. Here also, I should mention that I worked very closely with two eminent scientists in Hanover and in Spain, who are women, Professor Ana Sanpera and Professor Dagmar Bruce. And working with them, I also realized how to fight against this gender inequality in the society. So then I moved, as Himadri mentioned, to short in Jawaharlal Nehru University, where I met Himadri. He is my first student. I'm really proud of him. He did a very good work in this field. We will know more during my talk. And then I moved to HRI. So with this, I may continue the work that I'm going to present. As I said, that I will be talking about technologies. And the technologies that I'm going to talk are computer, and communication devices. So these two are probably integral part of our society now. And in this last year's pandemic, and still it's going on. So we realize more the importance of these two devices in our life, with respect to the communications, with teaching, in many other places. So communication devices can be broadly classified into two categories. One is communication without security. That means these communications, when you send information from one place to another, you communicate, you don't care about the security aspect. That means you don't have lock and key system to send this information. On the other hand, there can be communications where there is that's known as secure communications or cryptography. And here information is stored, and information is kept with a system of lock, and keys are available to only people whom we decide to get the information. And so our aim is to prepare a lock which is not breakable, or which cannot be used by any key, which cannot be opened by any keys. So I will talk more about this secure communication in later part of my talk. So what I'm going to talk here in next 1 hour is the quantum versions of these technologies. So let's start with a computer. So the technology based on quantum mechanics, this computer that we are going to build can be called quantum computer. So computer that nowadays we are using, like laptop and desktops, they are very useful, as I have told you. And these can be called classical computer, because the technology, the hardware and software, everything that we built, they are based on classical mechanics or classical electrodynamics, classical information theory. And so we will call them classical computer. Now, these computers are very useful. So this can be connected. So several computers can be connected and can build workstations where we can do powerful computation that we know. Now, these computers are very useful, and probably it's not required to emphasize the usefulness of computers, these classical computers, because they have use from educational field to hospitals, government offices, and many places. So they can be used to write documents, to use internet, to even for entertainment, to watch movies. So we know they are useful, but they also do some mathematical calculations that we are going to discuss now. And so by using these computers, we can solve certain mathematical problems, or we can address certain mathematical problems efficiently. Now, when we want to build classical computer, there is a basic unit in which it is running. They are bit, so one of zeros and ones. So typically, if we have an input that can be translated into bits, then certain logic gets been performed. And finally, we get the output, which again can be translated in zeros and ones, that is bits. Now, first problem that we are going to address is the following. These are called prime identification problems. So when I will give you a number and you have to tell me whether it is prime or not. So if the main goal is to design a program in a classical computer so that this can solve any arbitrary n-digit number. Now, although this problem looks very simple because we learn prime numbers in schools and even in our primary schools, but when it's an arbitrary n-digit number and we want to know whether the number is prime or not, this problem was unsolved till 2000. So it was solved in 2002 by three computer scientists from IIT Kanpur. And they found an algorithm by which you can solve or you can find this problem, or you can solve this problem within polynomial time. So what do I mean by polynomial time? Because if I want to solve certain problem, so if I want to solve this problem for n-digit number, then the time takes to solve this problem is order of n to the power alpha, log n, and so on. Now these are the three people. Now, so this is a good news that we can solve this problem in our normal computer with a reasonable time. That means with polynomial time. Now, the second question that we are going to address is the following, that is called prime factorization problem. So here we want to find prime factors of a given integer. Again, we know that this can be done very easily if we have a 2-digit number or 3 or 4-digit number. Even if I give you a 8-digit number, you can solve it easily. And this number, for example, it's an even number because the last digit is 8. And so we know, okay, this can be not so easy, but even with, a school child can do this factors, can find the factors. But if the 8-digit number, we making 120-digit or 100-digit numbers, then to write down a program which can solve, which can find out all the prime factors of an 100-digit number is not so easy. Just to give you a flavor that how difficult this problem is, if we use kind of 1600 workstations, and if we want to solve certain like 125-digit number, then it usually typically takes 8 months to solve it. And if 125 we can make double it, that means if I want to write a program in a classical computer, which are known as classical algorithm. So if we have the known classical algorithms, if we use, then to solve 250-digit numbers, we require almost age of the universe. Even if we have a powerful computer, as powerful computer as possible, so whatever is available till today. So this is kind of bad news. More accurately, if I want to tell, that to factor an n-digit number, the known algorithms which we can use in our classical computer takes exponentially n steps. To be very precise, it actually takes this number of steps. So we can probably tell that no efficient classical algorithm available till date. But in 1994, it was shown that if we use quantum mechanics, then we can solve this problem in a reasonable time. And this is known as Peter Shor, has USA mathematician. He proposed this algorithm and known as Shor's algorithm. So as I have told you, classical algorithm takes this many steps. On the other hand, if we solve this problem in a quantum computer by using quantum mechanical principle, then we require polynomial time. Actually, you require this number of steps. So this is Peter Shor. So this is indeed a good news, and during that period, several other algorithms are proposed where it can be shown that by using quantum mechanics, one can reduce number of steps required or number of steps that one used in classical computer and in classical algorithm. So these are Grover, Deutsch-Schwarzer algorithm, where you can show that, for example, classical algorithm can take n steps. On the other hand, if you use quantum mechanical principles, then one can reduce step to square root of n, 1, etc. So there are a polynomial efficiency increase can be shown by using quantum mechanics. But I should stress here that by using Shor's algorithm, we can show exponential speed up by using quantum mechanics. So as I have told you that in classical computer, the basic unit is bit. So it's either zeros and one. Now we want to understand that probably I have already convinced you that quantum mechanics help us to get a better efficiency. And so it's important to build a quantum computer. So if we want to build a quantum computer, what will be the basic unit? The basic unit is known as qubit or quantum bit. And this qubit is an arbitrary two-dimensional quantum state, which can be represented by geometrically by surface of the Bloch sphere. So mathematically, it can be represented by this, where up and down are the spin half systems, and alpha beta are the complex numbers. Now, just to tell you the basic principle that help to get this better efficiency in all these quantum algorithm are the superposition principle. So in classically, we can see a live cat as well as dead cat, but quantum mechanics tells us the existence of a state which is alive plus dead. So which is of this form that I have already mentioned. So alpha up plus beta down. And this is the reason for the success of quantum mechanics to propose this Shor's algorithm. So if we say that the success came due to quantum mechanical principle, or typically because of the superposition principle, because we start with a state which looks like that. This is our starting point, and that gives us a better efficiency, or that gives us to get this exponential speed up. So in a classical computer, we know the classical universal gates. They are AND or a NOT gate or NAND gate. Similarly, one can find what will be the universal quantum gates that one has to perform to do manipulation in quantum computer. So the basic single qubit gate that we require are Hadamard gate, and there are other gates also. And in 2 qubit, there are something called control NOT gate. As you see that if the first qubit is 0, then nothing happened in the second qubit. On the other hand, if the first qubit is 1, then it is flipped. Now this 1 can be represented by a spin half particle, by using spin degrees of freedom. So 0 can be a up spin and 1 can be a down spin. So in this way, we actually represented this transformation. And so we know these all operations are unitary, as we know these are the from our quantum mechanical basic postulates. Now the next questions, probably that this is the all theoretical prediction that shows that quantum mechanics gives us exponential speed up. Next question is whether there are some experimental realizations of these algorithms. Indeed, there are a lot of experiments going on around the world. So one of the recent experiment showed that by using ion trap, they realize 11 qubit quantum computer by using this ion, and they are able to perform a very high fidelity single qubit and 2 qubit gates that I have just mentioned. Similarly, there is a famous experiment in 2019 by superconducting qubit where they showed quantum supremacy. And there are a lot of debate going on this experiment, but at least they show quantum advantage by using superconducting qubit, where they create quantum computer, you can say, by using 53 qubits. And they demonstrate certain tasks which actually requires much higher time by using classical computer. And they show that by using quantum computer, you reduce number of steps. Now, how much the steps can be reduced, still it is controversial, but at least it has been established by today that you can surely can reduce steps, which may not be exponential, but which is surely something better than the classical computer can do. So there are a lot of technological quantum technology implementation timeline have been proposed. This is one of from European Union, and several technological giants like Google, IBM, Microsoft, Intel, who actually build the classical computers, they are now trying to build quantum computer or quantum circuits, and several you can get the update. So there are small scale quantum computer is already available. So up to 72 qubit quantum computer has been built by Google and several other companies. And so we are now trying to build a computer which consisting of a higher number of qubits, and that's under process. Here, just to mention that this is really a technological revolution, similar like from candle to electric or LED bulb. Making better classical computer do not lead to the quantum computer. This is completely different principle. So the normal computer is built on the principles of classical mechanics, classical electrodynamics, classical information theory. On the other hand, to build quantum computer, we require quantum mechanical principles, and we also require quantum information theory, so on. So this is really a technological revolutions that we are going to achieve. So now I move to the next part, which is communication devices. So first, again, the communication devices, there is also a revolution happen in last few years or last decades. As you see that a few years back, we used to have probably this kind of from typewriter to letter writing to our normal phone, and now we use laptop or internet mobile phone to connect each other. So there is already a technological revolutions that we can see. And now I will show you that if you use quantum mechanics, then we can get better efficiencies than the communication devices that we are using nowadays. So whenever we talk about communications, that involve at least two parties, Alice and Bob, and they are situated in two distant locations, say Kolkata and Allahabad. It can be Mumbai and Madrid and so on. Now, one of them is sender, another one is the receiver. It can be Alia, Barun. It can be two people, two normal people, or two kings. And sender wants to send some information from one place to another, to Bob's side. Now, these informations can be classical or quantum. So what do I mean by classical or quantum? Classical means that Alice wants to send some bits to Bob, or Alice wants to send some quantum state to Bob. Now, this quantum state can be a qubit. That means a two-dimensional, arbitrary two-dimensional quantum state. So let's discuss first that part. So this is known as quantum state transfer, and it's also called quantum teleportation. It was proposed in 1993 by these 6 people. Here, the task is to send an arbitrary quantum state to Bob. That is arbitrary qubit to Bob. Now, as I have told you, an arbitrary quantum state or two-dimensional system can be represented by the surface of the Bloch sphere. Now, in a sphere, there are infinite number of points. So we understand that if we use classical device, then to encode or to send an arbitrary quantum state, we require infinite amount of classical communication. That is infinite number of bits to send an arbitrary quantum state from one place to another. Let us now discuss whether we get some advantage if we use quantum device. So as I said, Alice and Bob, Alice share an input state phi, which Alice wants to send to Bob. Now you can think that you can put it in a box and send it. Now this box is such that it can keep the quantum property of this state. So we prepared the box in that way. And then Alice just sent it via courier, for example. But this is not allowed. This physical transfer of quantum state is not allowed from Alice to Bob. So what to do? Now Alice and Bob prepare a bridge between them, and this bridge is a quantum bridge. Actually, Alice and Bob share a 2-qubit state, which looks like that, which I have written again by using spin degrees of freedom. So this is up down minus down up state. So it is the singlet state. Now Alice performs measurement on her part of the shared state, that bridge, and the input state. After measurement, Alice sends measurement results to Bob, and these measurement results can be shown to be 2 bits of information to Bob. Now, how she will send the measurement result? Just by using phone call. And after this phone call, Bob performs certain unitary operation so that at the end of the day, Bob has the input state that Alice wanted to send. And you see that by using this protocol, actually, if Alice and Bob a priori share a quantum state, that is, if Alice and Bob share a bridge, then 2 bits of classical communication is enough to send an arbitrary qubit from Alice to Bob. On the other hand, as I have told you, or as I have argued, by using classical device, that means by using a state which doesn't have the property of the bridge, then that requires infinite amount of classical communication or infinite number of bits. So this was the protocol, and so this is really a good news, and it is known as quantum teleportation. It was discovered by these 6 scientists. Now it looks like something magic going on, but it is not, because the basic ingredient is the properties of the bridge that I have already explained. And this property is known as entanglement. So entanglement is a key ingredient to achieve this task. If you're interested about entanglement, the Horodesk is that already Himadri has mentioned. There's a very nice review article in 2009. It's in Reviews of Modern Physics. You can also see some of our recent review article on this subject. So let us define entanglement, because entanglement is one of the key elements for achieving or for obtain a higher efficiency in communication devices. So suppose I have Alice and Bob. So Alice wants to send some information to Bob, as I have mentioned. Now Alice prepares a state phi A and Bob prepares some quantum state phi B. Then the joint state looks like that. So if we have a complex number x and small x and capital Y, then this can be a thought of factorized state. And these are known as unentangled or useless state. So if Alice and Bob can prepare these states even when they are far apart, then these states are called unentangled states or useless state. And these state, if Alice and Bob share between them, so if this is the property of the bridge, then Alice will not be able to perform the teleportation experiment that I have described. And mathematically, it looked like that. On the other hand, entangled states that are useful for quantum teleportation, these states can not be prepared by Alice and Bob when they are situated in too far apart location. So to create an entangled state, we require a single resource or single source where this entangled state can be prepared. And after that, one particle should go to Alice, another particle should go to Bob, so that Alice and Bob share an entangled state. The definition is looks easy, but here I should mention that given a quantum state, still it is not easy to find whether a state is entangled or not. So still now we don't have a very efficient method which we can use to test whether a state is entangled or not. Now we understand that this communication, we can improve our communication protocols by using quantum mechanics. So probably we want to build quantum communication network. And in these directions we are working. And as I have told you, that entanglement is a key ingredient for achieving higher efficiency in quantum communication protocol. So when we want to build network, our primary aim is to share entanglement over large distance. And this is a real challenge. So one possibility is to divide the entire channel into small parts, and then we perform some quantum measurement in certain nodes, so that finally sender and receiver share an entangled state. Now, if they all are highly entangled state, one can show that sender and receiver can also share a highly entangled state. On the other hand, in a real experiment or in real communication protocol, these states are noisy. And so it is not so easy to establish a connection or establish an entangled state between sender and receiver. And this is one of the recent work, which is published just in December from our group, where we show that in a one-dimensional lattice, how to share entangled state. We give a proposal, as well as our proposal works for two-dimensional quantum network. So in these directions, we have also done certain work. If you are interested, you can look. Again, we come to the questions whether this is really a theory, or we have some experimental achievements which show that the communication protocols can be enhanced by using quantum mechanics. And there are a lot of experimental achievements in this direction. So by using photons, it has been photons, in case of photons, we use right-handed or left-handed circular polarizations. They are the ideal candidate for qubits. And it was shown, for example, in 2017, that by using satellite, they can share two entangled states between two cities which are 1,200 kilometers away. And this was experiment done by Professor Pan. And this was a breakthrough experiment because previously it was only shown about 100 kilometers. And this experiment actually showed that one can establish a quantum communication protocol over 1,000 kilometers. That means almost from Kolkata to Guwahati. Similarly, ion trap, also another important candidate for performing quantum computation and quantum communication devices. It was shown that 20 qubits can be entangled in an array by ion traps, calcium ions. It was the experiment done. Then by using other superconducting qubit, also 20 superconducting qubits has been entangled, and there are something called Schrodinger cat state has been realized. So there are several other physical systems which are the potential candidates for realizing quantum computations or quantum communication. So they are nuclear magnetic resonance, ultra-cold atoms in optical lattices, semiconductor devices, and so on. So as I have described, finding physical systems where quantum computer can be realized or quantum communications can be realized are important. In a similar fashion, one can say that finding useful physical systems where entangled states can be found are important questions in this field, or where we can build quantum technologies. For example, recently people have proposed that quantum mechanics can help to store energy. So as we know, in our normal battery that we use in several days, several machines, this battery stores electrochemical energy and converts it to electrical energy whenever required. Now it was shown that interacting spin-half model can act as a quantum battery. So for example, this XY spin model can act as a quantum battery. Then local magnetic field can be used to charge this quantum battery. And then we can calculate that how much energy we can store in this battery. And recently we have shown that if you use quantum mechanics, that means if you use quantum interacting Hamiltonian, then with the interaction strength, we can increase the extraction power or the storage power of a quantum battery. Moreover, we have shown that if you have impurity in interaction, then also the power can still be enhanced in this battery. So also in these directions, we have several work. One of the work was mentioned by our coordinator. This is his beautiful work where we have established genuine multi-site entanglement in isotropic spin lattices. So as I have said, these finding physical systems where quantum computer or quantum technologies can be built are important questions in our field. Now I end with the last part of my talk, where I will talk about secure communications or quantum versions of cryptography protocol. So what is quantum secure communications? Here, Alice wants to send some classical information to Bob securely. So Alice again wants to send some classical information to Bob, but now there is an eavesdropper in between them. Now, eavesdropper aim is to gather as much information as possible that Alice is sending to Bob. And Alice's aim, or the sender's aim, is to design a protocol in such a way that eavesdropper cannot gather information that Alice is sending to Bob. So there is a kind of trade-off relations between eavesdropper information gathering and Alice's strategy to send the information. And these secure communications are very useful in our daily life. For example, we use the similar technique for internet banking to do shopping through internet. And this probably also, again, we realized during our pandemic, the importance of internet banking, the online shopping, etc. But these secure communication at the same time are useful for national security, because from ancient time it has been realized that secure communication is an useful part in national security. Now, here the important point is that this classical cryptography security, or the classical cryptography, is very well established subject, and it's we know from our daily experience that all this online shopping, internet banking, they are very, very secure. I mean, quite secure. Although from time to time we get the information, so we get SMS that there are, don't answer the questions, don't answer, disclose your passwords with anybody, and so on. But the security of classical cryptography is based on the belief that some mathematical problems cannot be solved in classical computer in polynomial time. So this is the question that I addressed in the beginning of my talk. So for example, security of a classical computer is based on the belief that the mathematical problems like prime factorization problem cannot be solved in a normal computer, in our computer, in a reasonable time. Now, here is a twist that we know by using Shor's algorithm that quantum mechanics can solve this problem. So if we have a quantum computer, so if eavesdropper has a quantum computer, then eavesdropper can break all the classical cryptographic systems that we are using nowadays. So quantum mechanics can make all current crypto systems insecure. So what is the remedy? Now the remedy is the following, that quantum mechanics again help us to build a crypto system which remains secure till the validity of quantum mechanics. And we believe that quantum mechanics is valid. So quantum crypto system is secure even when eavesdropper has a quantum computer, or Alice and Bob, or anybody has a quantum computer. So these are known protocol by Bennett Brassard 1984 and Arthur Eckert 1991, where we generate quantum key by using sending, or Alice sending randomly generated quantum state to the receiver. And here eavesdropper, whenever eavesdropper wants to get the information, eavesdropper has to disturb the system, and quantum mechanical law ensure that whenever eavesdropper disturbs the system, then Alice and Bob can understand that, so that Alice and Bob can discard the protocol and start a new protocol. This is the good news of this quantum cryptography system. It says that disturbing of quantum states can be detected, and it was done long back by Utters and Zurek. These are the Bennett, Brassard, and Eckert, who have proposed the quantum key distribution protocol. So it's true that there is a, it is not possible. The disturbance can be detected in quantum scenario. But there is again a trade-off, because the information that that eavesdropper can get, and the Alice and Bob, the design of the protocol, so that the information that is flowing from Alice to Bob, this information and the gathering of information by eavesdropper, these two information has some trade-off, because discarding the protocol is costly. So whenever Alice and Bob understand that there is an eavesdropper, if they discard the protocol, then that will actually that make the system very costly. So there are a lot of work going on. So here again, I mentioned that there is a cryptography system is quite well advanced. There are a lot of experiments. So the initial experiment, even in 2001, where they are able to do a quantum crypto protocol between two sites of Geneva Lake, Lausanne and Geneva. And there was a football World Cup at South Africa, where they are able to protect. They have something called Quantum Stadium project, where they use quantum crypto system, and they distribute secure key between two places. One is the stadium, another is the joint operation system, to protect the informations from the betting. There are Geneva elections where also they have used quantum crypto system. So here I just want to mention that, as I have mentioned, there is a trade-off between the information gained by the eavesdropper and the information flow from Alice to Bob. This part is still, there are a lot of work. This has some importance or implications towards the security of quantum cryptography. And in our group, we have found complementary relations, which provides a bound on the secret key rate on a quantum key distribution protocol. We also work on monogamy of quantum correlation measures extensively. So there is also a book chapter we have written by some of us, and also with Himadri is a co-author of the book, where we talk about monogamy of quantum correlation measure, which actually tells us that if sender and receiver shares an entangled state, then eavesdropper, how much eavesdropper can be correlated with sender and receiver. This trade-off between the entanglement shared between sender and receiver and the entanglement between sender and eavesdropper, or receiver and eavesdropper, this trade-off, we talk about that trade-off in the subject called monogamy of quantum correlation measures. And in this group at HRI, we extensively work on this problem. Recently, we have found no masking theorem, where we showed that quantum information is hidden, can be hidden from subsystem and spread over quantum correlations. This is not possible in case of quantum information, although such if quantum can be replaced by classical, that means classical informations can be hidden from subsystems, and but quantum informations cannot. So masking is not possible in general for quantum information. And this also has some implications on quantum cryptography involved with several parties. With this, I come to the end of my talk. So I think I am able to convince you that we are going towards, or heading towards, a new era. We can revolutionize our computation and communication capabilities by using quantum mechanics. Now, these communication capabilities can be with or without security. And so quantum cryptography, as I have told you, it's already a reality. So now there is a question of quantum internet or quantum communication network. People are trying hard to build over the world, around the world. And then probably we have small scale quantum computer already that has been built, which is around 100 qubits. But to really show that Peter Shor's algorithm is more efficient than the classical algorithm, we have to build a computer consisting of around 1,000 or more than 1,000 qubits, which is really a technological jump which people are trying. And there are a lot of predictions that probably we will be able to see quantum computer in next 15-20 years. And I have already shown you that not only these technologies, but there are several other technologies can be built by using quantum mechanics and can be shown to have more efficiency, like energy storage device that we have discussed. There are several thermal machines have been built where we can show that quantum mechanics can help to get more efficiency. With this, I come to the end of my talk, as all the results that I have presented cannot happen without my students and the postdocs working with me. So already Himadri is here, who is the coordinator, and I think also in Zoom there are several of my students. So Tomogno, Debashis, Tishtas, they have already defended their thesis. They are doing postdocs in Europe. and Himadri has just come back to India. I'm really happy. He will be a faculty in IIT Bombay. This is my current group where I have around 5 students and also 3 project students, Pritam, Tona, and Oyo. They are also working with me. And all the works that I have presented are done by Shoptoshi, Ratul, Ganesh, Vibhu, and Sijan. Without them, it's not possible. I also work extensively with the postdoc Shiladitto, and he now moved to a different country. And Amit Kumar Pal, he is a faculty in IIT Palakkad. So without them, it is not possible. All the results that I have presented, thanks to them. And this is the entire group, QIC group at HRI. So currently we have 15 PhD students and 5 students are doing projects. So hopefully they will join the group. Hello?
Sorry, there was some disturbance, Aditi. Sorry, please go on. Aditi?
Hello?
Yeah, can you please go on?
Hi, Aditi, I think there is some website or something open which you need to close probably.
Hello?
Yeah, it's fine.
Yeah. So there is something, some noise came. Okay, so with this, I think you can view the full screen, right?
Yes, view is fine. Yeah.
Yeah. So there is, so this is the student, and there are 5 postdocs and 3 faculty members at HRI. And thank you very much for your attention. I'm sorry that there was some disturbance came. I don't know how. Thank you very much. So I can take now questions.
Yeah. So should we start with the questions on the chat first, or like, does anyone have a question right now? Maybe you can just ask. Like Professor Nanal, like, can people unmute themselves and ask a question if they want to?
Yeah, sure. That it's up to you. You can take care of that. If they can unmute and ask question, you can in the meantime take something from chat and come back here, whichever.
Okay. Yeah. So I'll just wait for 15 seconds. If anyone attending the talk has a question, you can just unmute yourself and raise it. In the meantime, I'll be reading the questions in the YouTube channel. Yeah. Okay. So Aditi, I'll start with the questions in the chat in the YouTube channel. So the first one is by Abhinav Chaudhary. And what he wants to know is, what is the main reason we typically do not use the electron qubit as a data qubit in a quantum algorithm?
No, you can use. That's not, I think you can also answer this question nicely.
Yes.
So I think you can use, I mean, I have used, I have illustrated with certain degrees of freedom of photon like polarizations in ion trap, the internal levels of ions, etc. But there are other possibilities which I haven't ruled out. So
yeah. So Avinav also has a second question. I'm not sure whether it's very relevant for this particular talk, but he wants to know if you can determine the absolute neutrino mass using quantum technologies.
There is, okay, I also don't know much about that, but there are some work going on where at the interface of high energy physics and quantum information theory. So people are working towards that, but yeah, I exactly, I don't know the answer of the question. So.
Yeah, so the next question is by Ravi Chinappan, and he wants to know the idea of sending a quantum or entangled state is not very clear to him.
Idea of sharing?
The idea of sending a quantum state or sending an entangled state is not clear to him. So
Ah,
I'm not
uh,
sure which specific part of the talk he's referring to, but yeah, it's a
yeah,
general.
yeah. So I think, yeah, I mean, sending entangled state means that you have a quantum channel, and by which you actually, in case of, okay, if probably when I said that sharing of entangled state, that means, say, if we use a photonic system, then there is a parametric down converter is one way to share entangled state or create entangled state. You put laser on it, then there are two photons which will be entangled. And that one photon, I mean, they will be through a channel, either through an optical fiber, or this can be a free space experiment. So that is mean there are, and mathematically it will be through some channel, quantum channel.
So there is this another question by Basavaraj Kagali, and I think the first part is something you already answered, but I'll still rephrase it. Like I'll still restate what he said. So the first part he says, could you explain how quantum entangled states can be exchanged between two persons without being intercepted by others due to the wave nature of quantum mechanics?
Okay. Yes, I mean, he said that two particles can be interchanged. This is the question.
Yeah,
Interchanged?
no,
Or maybe they want to mean this sharing only.
yeah. So I think what they mean is like when you're trying to share the entangled state or send it somewhere, how can
Yeah.
it be intercepted, or how I think like how decoherence takes place in general, maybe.
Yeah, so that, yeah, that's true that there will be most of the time in case of photon, I mean, you know, if it doesn't reach to the detector, then that is either for different reasons. Although photon doesn't interact so much with other particles, that's a good part. But in a free space experiments, it's hard to detect photon, because in this parametric down converter, for example, you don't know whether two photons are coming out or zero or something. So this is one problem. On the case of ion trap or other experiment where you trap the ions, there are different kind of decoherence that is coming into the picture. And in all these situations, it's true that many cases the way I have presented is the ideal scenario, or I should say, theoretically, we usually say that these are pure entangled state and so on. Typically, it will be a mixed entangled state, which I haven't at all give the definition, because this is a general talk, so I haven't given the definitions. Typically, the entangled state will be mixed, and it is a big challenge to keep coherence, or to, I mean, when you share entanglement, at the end of the Alice and Bob really shared the entangled states. That is a different questions. And as I have already give a hint that given a quantum entangled states, or given a state, we still don't know proper or efficient detection criteria by which we can conclude that the state is entangled. That we still don't know. I mean, there are several by entanglement witness, etc., but not in efficient way, I should say. And when you have more and more parties, things become more and more difficult.
So there is one more question. That's the last question from the YouTube channel. Sorry, Aditi, were you speaking or? Oh, okay. Yeah, one last question. It says it's again by Basavaraj Kagali, and he wants to know: could you explain the show's algorithm in a simple way?
Oh, that's a difficult question, because I think it's, I mean, it's a very, I mean, it's not so easy to explain in just two lines. It's used something called Fourier transform, and as I have mentioned that you have some initial state. This is the probably the Shor's algorithm is one of the difficult algorithm to explain even in a class. So you require certain basic ingredient to start with, but very naively it says it uses the quantum superposition states that I have already mentioned in my talk. That's a basic ingredient, and then you perform several gate operations which I have again mentioned, and after that you will be able to realize.
Yeah, I think to add to that, it's something not easy to answer even in a question paper. So
Yeah.
it's difficult to say.
That's why I said even in a one class, it's not possible to teach. So it will be very hard to tell. So I can
Okay.
only tell about the ingredients.
So there is one more question in the YouTube chat which just came right in. It's from R. Ramachandran, and he wants to know. He's saying, "Am I right to understand we have quantum cryptography available for a potential cracking by quantum computer?"
Yeah, it is true, but there are several other tracking issues which are not still we don't understand. So most of the attack that we people are testing are the coherent attack, where usually people assume that one by one photon is sending, Alice is sending to Bob, and eavesdropper is attacking, or whatever protocol eavesdropper is designing, which is actually when the one photon is passing from Alice to Bob. But when suppose there is a quantum memory available where Alice is sending one photon, I mean one by one photon from Alice to Bob, and eavesdropper keeps this photon for some time, and then after that eavesdropper design a protocol and do something, then there are several complicated scenarios can be thought of. All these scenarios haven't been exploited, and that's why there are several open questions still remain. As I said, that it's true that the quantum mechanics help us to understand that when eavesdropper is present in the channel, and so we can detect them. But whenever we detect, if we discard the protocol, that will be extremely resource wasting scenario. So we want to get a strategy where we want to get a trade-off between the information that is flowing from Alice to Bob and the gain that is done by eavesdropper. So up to certain information gained by eavesdropper should be allowed, so that still the entire protocol remains secure. So there are a lot of so the eavesdropper strategy are also important part when we study cryptographic system. This is for classical as well as quantum. So several quantum scenarios can be thought of. Some things are already done, and some protocol based on that protocols, quantum crypto machines are available, and there are people are trying also other kind of security systems to be explored. Even theoretically they are not known.
Okay, so I think that's the entire list of questions that we had on the chat. So for our YouTube viewers, I think Professor Nanal just added a comment with regards to uh, work of using entanglement to detect neutrinos, which was given by Ganesh Tlakaraju on the chat on Zoom. So yeah, if you're interested, just check that out. So I would keep the floor open for anyone in the Zoom meeting if you have any questions.
So I stop sharing because
Yeah. Okay. Yeah.
May I ask something?
yeah,
Yeah.
sure.
I think it may be nice, Aditi, just some one word of advice for somebody who's going to be starting in this field, the research.
Yeah, so if you have a basic quantum mechanics prerequisite, I mean basic quantum mechanics knowledge, one can start this subject. There are several because the quantum technology, when it started, at least when I started my research career, people tried to convince people that the quantum mechanics really help to build technology. So there are several notes are available, and now probably several I mean teaching materials are available in the web, so people can start, even the homework can be started. So
Yeah, because it's a very upcoming field and people are also keen on that. So I think the message is that there are plenty of opportunities, and just with a basic quantum mechanics background, you'll be right into get into
yeah,
that.
so in this aspect I just want to mention one can check the Harishchandra Research Institute website, where there are a lot of lectures available on quantum information and computation, because we usually teach in our MSc and PhD program quantum information and computation 1 and quantum information and computation 2. So for example, there are two courses available. One is a basic and one is more advanced, where we covered these quantum computations, algorithms, and so on. And in the first part, mostly the basic things like communication, etc. So if you are interested, you can also look at that.
Yeah,
And
that's, I think, very, very nice. They can look up the basic course and so on.
yeah, so that's also available, and also people can contact anytime to me, write to me, and I'm usually available and try to answer as much as possible.
Very good. And your address again is also available on the website of
Exactly.
the HRI. Yeah.
So,
So,
Aditi, I'll just end with one last question to you. So, it's a very general question. So, from the time you've come to India, how do you think that the field of quantum information and computation has developed in terms of both theory and experiments?
No, it's true that when 2009 I came back to India, there were not many groups at all. I mean, there are only few groups who are really working. And it's a very nice situation that now several people are working. And as you know, that government also have some declaration and of huge money for investing for quantum technology. DST, Department of Science and Technology, has some initiative. But I think we have to go a long way because, as you see, for example, China, Europe, America, they are quite far ahead if we think about experiment. So we have to, I mean, we are just starting now, but I still think there are, as you know, as also as a researcher, that there are several I mean several areas which are now opening, like this storage device, thermal machines. There are several technologies that the people are trying to build. Every day it's coming new area, and new interface are coming, so there are several opportunities. So although we are late, but if we are a bit enthusiastically address, then it's true. But several new scientists like you and several others recently have come back to India and building their own group, and that's really a big enthusiastic scenario.
Okay. So, with that, I'll probably end the session, and I'll thank Professor Aditi Sende on behalf of everyone who attended the talk, and from Professor Nanal for attending this wonderful webinar. So, Professor Nanal, I'll hand it back to you to.
thank you, Dr. Madri and Professor Aditi, for really a wonderful and inspiring talk covering such a complicated subject in a simple way, and also making a lot of resource material available to all those interested. Thank you, Dr. Himadri, for doing this in such a critical stage of even being in quarantine during this talk. And this is kind of, one of those things where Murphy sort of puts a stopper, and yet we still made it. So we actually, it also happened on a nice occasion. And thank you all, the audience from Zoom and YouTube, for joining in for this lecture. I would like to remind you to join us back next Saturday for 25th lecture. It will be given by Professor Shobna Narsiman. So see you all next week. Stay safe, take care, and see you. Bye bye. Thank you.
Bye bye.
Thank you.